and welcome, and in this video we're going to be talking about completing the square, okay, which is another way that we can use to solve quadratic equations. Now, if we were given a quadratic equation, the way we would try to solve it first is by factoring, because that is generally the easiest way to solve a quadratic equation. If it can factor, it's a lot easier to do it that way. However, for this problem, we would actually run into a bit of an issue because we would have to find two numbers that multiply to 10 and add to 12, and unfortunately, there are no two numbers that do that. Well, there's not two nice numbers that do that. So we actually cannot factor this, but that doesn't mean that we just give up and don't solve it, because there are two solutions to this equation. Now, when you cannot solve by factoring, there's a couple different ways you can do it. You can use a quadratic formula, which we'll be covering a little bit later, or you could actually complete the square, and that's what we're going to cover here. Now, completing a square is the process of adding a constant to each side so that one of the sides becomes a perfect square trinomial, because then you can factor that and actually just take the square root to get rid of the square. And that's generally what we do. So I'm going to walk us through the steps of completing the square. Now, the first step is we need to have a leading coefficient of 1. Right now, we have a leading coefficient of 2. I have 2x squared. I cannot have that. I need to have that be 1x squared. Can't have 2x squared. Can't have negative 4x squared. It needs to be 1x squared. So the first thing you're going to want to do is you're going to want to divide each side by the leading coefficient. So in this case, we divide each side by 2. And once we do that, we might end up getting fractions here and there, but don't worry, fractions are just numbers too. We can treat them as such. So we end up with x squared plus 6x plus 5 halves is equal to 0. Now from there, what we want to do is we want to move the constant over to the other side. So we're going to subtract 5 halves from each side. And once we do that, we get x squared plus 6x is equal to negative 5 halves. But I like to leave a little space, because now is a process of figuring out what we need to add to each side to get the left-hand side to be a perfect square trinomial. Now, the way we do that is actually pretty straightforward. The first thing that we do is we take half of the linear coefficient. So the linear coefficient is 6, so I'm taking half of that, and that half is 3. Then we square that number, and that is what we actually add to each side. So we take half of the linear coefficient 6, which is 3, square that 3, and that gets us 9, and we're adding that to each side. Because we're squaring this, this is actually creating a perfect square trinomial. So as we can see, we now have x squared plus 6x plus 9, and that is a perfect square trinomial. That would factor to x plus 3 and x plus 3. So I can write that as x plus 3 quantity squared. And this is where completing the square really is useful, because now what we can do is I can take the square root of each side. And that will allow me to solve for x finally, okay? So what we do is we take the square root of each side, because what happens is the square root and the squared here are going to end up canceling out, leaving us with just x plus 3 is equal to plus or minus the square root of 13 over 2. Remember, it's always plus or minus whenever we take the square root of each side. And another thing is we actually cannot have a fraction inside of a square root, because that's the exact same as having a radical in your denominator. So I like to split it up. The square root of 13 over 2 is the same as the square root of 13 over the square root of 2, because we're going to have to rationalize that in a second. Now from here, we can go ahead and solve for x. So I'm going to subtract 3 from each side, and that's going to get me x equals negative 3 plus or minus the square root of 13 over the square root of 2. And from here, sometimes you're going to be done. If you don't need to rationalize this, you're done. However, we do have to rationalize this because we're left with that square root in the denominator. So remember, all you have to do is multiply by the square root of 2 over the square root of 2, because what's going to end up happening is this denominator is going to become the square root of 4, and the square root of 4 is 2. So square root is gone. So our final answer is finally going to be x equals negative 3 plus or minus the square root of 26. That's from multiplying these two over 2, because that would become the square root of 4. Square root of 4 is 2. And that would end up being our final answer. And that is completing the square. Now let's go ahead and take a look at just one more problem, because all completing the square takes is a little bit of practice. Okay, so let's take a look at another problem. So let's say we have this one here, 3x squared plus 12x plus 21. Now, once again, we could try to factor this. However, this would actually not be factorable. So we're left with either the quadratic formula or completing the square. You know what I'm going to do? I'm going to complete the square. I actually like completing the square more than the quadratic formula. Don't ask me why. I just think it's a little bit quicker. I don't know. So we would start by, once again, getting rid of the leading coefficient. So we need a leading coefficient of 1, so we divide by the leading coefficient 3, and that gets us x squared plus 4x plus 7. And now you might be able to really see that, yeah, there's no way we're going to be able to factor this. So remember, from here, what we do is we move the constant over to the other side. So I'm subtracting 7 from each side. I'm going to leave a little bit of a space because I know I'm going to have to add something to each side as well to form this perfect square trinomial on the left-hand side. Now remember, to get that, what we do is we take half of the linear coefficient. So I'm taking half of 4, and that gets me 2. And then I actually need to square it, hence complete the square. So I need to square that number, and 2 squared is 4, so I'm adding 4 to each side. Total coincidence that these are the same. Don't try to associate that, okay? We always take half of the linear coefficient, square it, and that's what we add to each side, okay? We add 4 to each side, and now what happens is this is now a perfect square trinomial. X squared plus 4x plus 4 could be factored to x plus 2 and x plus 2, which is x plus 2 quantity squared. So this actually becomes x plus 2 quantity squared is equal to -3. And now what we're going to have to do is we're going to have to take the square root of each side, okay? Because that is going to cancel out the squared here, which allows me to solve for x, okay? Now when we take the square of each side though, or the square root of each side, excuse me, I'm left with now plus or minus the square root of -3. Remember, in the real number system, we cannot have a negative underneath the square root. However, we talked about imaginary and complex numbers, so this means that our solutions are actually going to be complex numbers that are part imaginary, okay? So since there's a negative underneath the square root, what's going to end up happening is I am going to take an I out of that square root, because remember, the square root of -1 is I, so I can take out an I, and that now becomes the square root of +3. That is how we take care of negative square roots. We pull an I out in front of the square root, and what's underneath the square root is now positive, okay? So that's where imaginary solutions come from. And from there, it's pretty straightforward. I'm going to subtract 2 from each side. I'm going to subtract 2 from each side, and that ends up getting me x is equal to -2 plus or minus I root 3. And if we can simplify this at all, make sure that you do. If this was like the square root of, say, 12, make sure you simplify that to become like 2 root 3, okay? But we can't simplify the square root of 3, so that would actually end up being our final answer, okay? Let's take a look at just one more problem. Okay, so let's take a look at this last problem here. So we have x squared minus 3x minus 12. Once again, we cannot factor this, so we could go ahead and complete the square. Now remember, to complete the square, we need a leading coefficient of 1, and in this particular problem, we actually already have that. All right, so we don't have to divide by the leading coefficient because it's already 1. So we can go straight to moving the constants over to the other side. So I add 12 to each side, and that's going to leave us with x squared minus 3x is equal to 12. Remember, I like to leave a space on each side because I know I'm going to be adding something to each side in just a moment. So remember, to get that number, we take half of the linear coefficient. So I'm taking half of -3, and half of -3 is -3 halves. Don't write that as -1.5. That's going to make it a little bit more confusing than it needs to be. Leave it as -3 over 2. That's -3 halves. And then we square that number. So -3 halves squared is 9 over 4. So that's what I'm adding to each side, 9 over 4. And now we have to go ahead and factor this. And factoring that would actually kind of suck if you had to. But remember, half of the linear coefficient is always going to be the number that you end up having inside of that binomial. So I know that it's going to be x minus 3 halves squared is equal to 57 over 4. That's just by combining 12 and 9/4, okay? So I have x minus 3 halves squared is equal to 57 over 4. And that's the beauty, remember, of completing the square. Because now all I have to do is take the square root of each side. And remember, when you take the square root of each side, it is plus or minus. Well, I take the square root of each side, and the squares cancel the square root. And I'm now left with x minus 3 halves is equal to plus or minus the square root of 57 over 4, which remember, I like to split up and have as the square root of 57 over the square root of 4. And this is a nice problem because we don't have to rationalize this one. Because the square root of 4 is just 2. So I don't have a square root left in our denominator anymore, so it's actually pretty much set up ready to go. Because now all I have to do is add 3 halves to each side, And that ends up getting us x is equal to 3/2 plus or minus the square root of 57 over 2. And we could have this written as our final answer. Just know since they already have the same denominator, we can write them as one big fraction. We can write it as 3 plus or minus the square root of 57 all over 2. Only because they have the same denominator. You can write it either way. You can expect to see it written either way. And that would end up being our final answer. So that is completing the square, and we actually can use completing the square to prove the quadratic formula, and that's what we will be talking about next. So I hope this video was helpful. If there's any questions, please feel free to let me know, and I look forward to seeing you guys in the next video.